Great, thank you. It says I still have a break of, oh, never mind. Time start again. Okay, so I'm actually a security scientist at H2O, what I'm going to be talking about today is the process that we adopt and how we go about analyzing issues in security using machine learning. And this is based off the talk that I'd actually done about a month ago in Atlanta. So, you know, some of you might be familiar with what I'm talking about. And the idea here is that I'll introduce more to the process of how we go about providing actual solutions that can be deployed. And a bit of the initial aspect, more like a preamble of what I'm going to talk, will be about what are the different kinds of attacks and how can you classify security attacks. So if someone has any questions, please, you know, you're welcome to raise your hand right away and ask me. But if we're losing time, then I'll probably hold you off till the end. Is that okay? Okay, great. So one of the first things about different kinds of attacks that you can classify is you can classify attacks in terms of short-term and long-term attacks. And what your short-term attacks do is the simple attacks, not necessarily, you know, having a bigger objective. It's usually to, you know, destroy some kind of a service. It's usually to stop something, or it could be physical attacks as well, you know, where the power of your building is shut down, or your network is cut off, or something like that. On the other hand, long-term network attacks, or long-term attacks, cybersecurity attacks itself, could involve network recon, enterprise service attacks, you know, attacks on infrastructure, some amount of phishing. You could see some spear phishing as well. A lot of social engineering, because it's easy to send someone an email and say, hey, give me a password, and he'll actually give it to you. So I know, I do it, so yeah. And so if you kind of break down the anatomy of a short-term attack, as I said earlier, it's super simple. You know, you identify a target. Who do you want to break down? For example, we can take an attack that actually happened on something called as some of the DNS servers that exist around the world. It was a simple attack, you know, where all the bots across the almost across the world were charged towards attacking DNS servers, you know, just to slow it down. There was no purpose. It was merely to slow down DNS services, and that was a big deal. Now, so you identify a target. It could be DNS in this case. You know, it could be your DNS servers across the world. You identify the kind of attack. In this case, it's a denial of service attack, and then you overwhelm the service. That's about it. It's very straightforward. Now, what are the kind of things you would see when a short-term attack happens? So the idea is the mechanism's super simple. You know, you gather a bunch of people who'll keep shouting on the network and, you know, bring down service. Simple. The variations usually occur in terms of protocols, in terms of how you attack. So I could do, you know, I could use protocols like DNS. I could use protocols like Finger. Any of these things basically to stop a service. That's good. I mean, the network's out. So they're short-lived. Your damage is very quantifiable. 100 machines down, an entire, you know, a subnet is down, or an entire network is down. That's about it. Now, on the other hand, your long-term attacks is something that you need to be worried about much more, you know, than the short-term attacks. The reason is because the way this happens is, and this is what you guys actually see, you know, most of the time in news right now. Anybody heard of Equifax? Maybe? No? Yes. Okay. Yeah. So something like that, you know, goes on. You identify a target. There's a long-term, you know, spread as to how you want to go about figuring out how to break in. You identify the target. There's super amounts of recon that actually happens. Recon can happen by state actors, you know, individuals, any of these things. There's something called as APT. I'm guessing a few people out here have heard of APTs. It's called Advanced Persistent Threat. State actors get involved. You know, there's a lot of money behind it. Countries are investing in a lot of these things, unknowingly, by the way. And a lot of recon actually happens out there. They go about identifying vulnerable infrastructures. You know, they contact you through email saying, hey, we're selling you this for like 80% discount. Do you want to buy it? Then you give them a credit card. You never know. They'll keep all those things in their database. And using those kind of attacks, they actually get a network foothold. So they get into your corporate systems. They get into your environment. And they do not destroy anything. They're very calm about it. they'll sit there for years. They'll sit there for like 6 months, 1 year, 2 years. But what they do when they sit there is that they explore the network. They explore what all resources you have. They explore if you have social security numbers, on your network, on your database for that matter. They explore if you have interesting information, about users. Let's say, you're one of the, you work with the military, you're a contractor. A lot of those information could be on your network. They explore for all that kind of information. And then what they do is they also have something called as a lateral movement. So in lateral movement, you actually get a foothold and you go around the network, try to figure out, where are the other vulnerable machines and things like that. And then they go about and they exfiltrate data. So data exfiltration is a very common thing. You don't necessarily figure that out when it's happening on your network, because any enterprise network is seeing so much of traffic, data exfiltration doesn't pop up. And the way they usually do it is, most of you people, anyone who used to use 56K modems to download stuff, like a whole game, I'm guessing people used to. So they usually download exfiltrate data at that rate, so you never see it on your radar. That's how cool it is. It's not cool, just, so basically, they do all those kind of things. Now, when you look at an attack, what they would have usually exfiltrated a lot of data. They would have figured out a lot of things about you. They would have placed a lot of bots on your network. Nothing would be in plain sight. And then usually you discover that a huge amount of your database is destroyed or it's siphoned out, and then you think that the attack's done and you're safe. It's usually not the case. It's usually an illusion because most of these attacks tend to have secondary backdoors, tertiary backdoors, and things like that. Basically saying that they have different levels of access back into your network even if you remove them. So, which is why the attack might still persist. There are tons of variations that you could use. You could have VLAN segments that are open, that you do not know about. You could have network ports in a lot of different points in your office. And this is something that I have actually personally seen when I've worked with a lot of organizations. You actually see network ports which are open and live, and I could connect to it and I could get somewhere on your network. It's kind of very unsafe, but people still do it. And these are usually like very long term. Now, if I were to say, can you give me an estimate of the damage? Super difficult, because I do not know, what your target is. I do not know what you're seeking. In the first kind of attack, you are seeking pure destruction. There's nothing else, just pure destruction. In this, you're not seeing, you do not have those kind of, simple factors that motivate you. Here, you're looking for, information. You're kind of leeching off everything that you can get from the organization. So your motives kind of change. So the assessment of the damage has changed too. So which is kind of a very difficult position to be in. So does this mean we focus on the long term? Not exactly. And the reason why is because the way usually attacks happen is there are short-term attacks, and then there are long-term attacks. And the idea is short-terms are usually used to blind you when a long-term attack is actually happening. And the idea is they usually run this together. Short-terms also tend to do some amount of recon. They try to help you, figure out what is happening on your network, what are the interesting things on your network and stuff like that. And which is why it actually becomes super important for you to look at both of these kind of attacks. Now, there is another problem. And the problem is there's tons of data that's coming into your systems, with your short-term and your long-term attacks. How do you actually look at it? What do you do with that data? And that kind of becomes a bigger question into what you look for. There do exist solutions, by the way. I mean, I have to justify at least this part of it, that they do exist solutions right now in the market, which do these kind of interesting things. But a lot of them are rule-based, they're limited. There's some amount of correlation in terms of time and in terms of data. You do not necessarily have like a contextual correlation. If you can say this data was exfiltrated, 180 days or 300 days after this server was broken into, kind of the correlation does not necessarily exist. And that ends up being a problem, when you're running with heuristics, rule-based systems for cybersecurity. So, which is actually one of the most important things for cybersecurity is that you have to be able to correlate these events. And correlation is super important. And a lot of people, I think not necessarily from the field of cybersecurity itself, who use machine learning for that matter, would also be in this situation. I mean, there are lots of business use cases, where you have to be able to you have to be able to correlate events. You want to find out, how can I associate these two things together so that I can get a good signal? And that's an important thing. No, that's not what I would suggest, but it's just up there. All you got to do is you got to use smarter algorithms. You build up smarter models. Try and identify what are the things that you can put into your model so that you can identify these behaviors and try to prevent these kind of attacks from happening. So the way I approach the problem is kind of very simple. I'm sure most of you probably take the similar path. Most of you probably do the same kind of thing. We go from a rule-based model to a feature-based model to a pure data-driven model. And the idea here is that rule-based model actually already exists, which is the current systems that are running on heuristics, current systems that are basically identifying any kind of interesting behavior. And I would like to classify it as interesting because most of the rule-based systems tend to be stateless or have state only for a certain amount of time, 30 days, last 30 transactions, last 30 transfers, and things like that. So when you move from a rule-based to a feature-based, you're actually forcing your data to encode all the behavior that you're seeing or all the state that you're seeing into an actual variable, literally in the form of a matrix. And that's when it actually becomes important to build that kind of a model. And if you look at features, and the reason why I stress on features is that features are kind of the metadata from the data that you exist. And all of us who have tried any kind of machine learning modeling for the first time, literally for the first time, you take whatever is in the database, 10 columns, 15 columns, and you throw it to a machine learning algorithm and say, show me something. Nothing comes up. Yeah. But then, that's where you start engineering good features. You're like, okay, I didn't see anything. Let me see if I can improve this. Let me put a ratio. Let me put some kind of a difference. Let me see if there is any kind of correlation in the data. Let me do a transformation. And that's where it actually becomes important for you to capture that information. And that is what your algorithm wants, because your algorithm needs this kind of information to be able to understand what the data contains. So if you were to put it a bit of, in a philosophical sense, it's kind of a language translation between the algorithm and the data, the raw data itself. And this kind of helps you build much better models. So your features are actually very important. Feature engineering, as a matter of fact, is very important. I think in the afternoon, I had a gentleman who was asking me, I think from Airbnb, who was asking me, can you tell me how H2O does feature engineering? And we had a long discussion. I'm not sure if he's in the audience. I can't kind of see him. But we had a long discussion about how it's important to identify the right kind of features that provide you, a signal in the end, or helps you identify your model. So coming back to the domain of cybersecurity and how we use AI. So some of the data sets that we use to build our features, like past attack behavior. This could be any source of data, where you've seen past attacks, you've seen traffic, you've seen interesting traffic. And this could be raw data as well. This could be literally your network capture, your log capture, endpoint device capture. Any of these informations actually add value. Your enterprise traffic, application logs and syslogs and all your IDS. IDS is intrusion detection systems and intrusion prevention systems, and those kind of things actually help you a lot in modeling this. So some of the features, that I've just giving you an example, fairly to give you an idea of the kind of features that we work with. Some of them are like average length of the connection, average number of DNS requests. DNS is like domain name service for people, who are not necessarily familiar with it. So you're looking for domain churns, you're looking for MTUs. MTUs stand for maximum transmission unit, which is basically the size of, amount of data you can send at one time in a network pipe. Your packet utilization is how much of the space are you letting go, every time you transfer a block of data. Window size is basically what is the capability of your network, how much data can it handle at a given point in time. And then arrival jitter variance. So one of the most interesting things about networks is the jitter variance. And That basically is a kind of feature that tells you what are the other things that are happening in a network. What are the interesting variations that are happening in a network, which is identifiable purely by the variation in time. So that kind of is a very important feature as well to tell you. So if there's an attack, you'll know because that time actually increases linearly. So some of the other features that we actually have is across multiple days. So we look at this is like a rolling average feature that we look at, kind of like a feature that helps us identify variations in spikes. And the idea here is that you have a feature that's identifying average TCP connection length across the last 7 days, but it's doing it every day. So today, last 7 days, and tomorrow, and the last 7 days, and so on. So any variation, this feature will help me pick up a spike. It'll tell me, if the average TCP connection length has it changed? Has it varied much? Has it not? So these are some of the interesting features that we actually put in as well. So some of the advantages, they highlight your transactional behavior. They're helping us, continuously track traffic across the network. And the most interesting thing is your rule-based models are purely threshold-based. So you say, this is 80%. If it goes above 80%, yes. If it doesn't, no. But here, what you're doing is you're actually building the model in such a way that it understands any small variations in spikes, and which is like super important when you're actually building a good machine learning model. So this has helped me every time. Probably subjective, but this has helped me every time. So some of the advantages, in feature-based model is we use AI. I know a lot of people, might debate that it's not necessarily AI, it's purely machine learning. I agree with you. It's just there. So the usage of these features are actually super consistent. They're actually very helpful in objectively identifying what your point of your most important thing. The classification is quick. We have a low false positive rate. Now, these are some of the successful things that we have identified: denial of service, recon, exploits, command and control traffic. This is mainly bots across the network. So I spoke about all this, but I didn't tell you how we label it. And one of the biggest problems in network data is, how do you know you've been attacked when you never know you've been attacked, right? That's the biggest problem. I'll quickly breeze through this because I have 2:30 right there. So the way we do labeling is you can do it two ways. One is a complete manual labeling process, and the other one is some kind of an assisted labeling process. And this might be, you might be able to, this is transferable for other business use cases as well. In a manual labeling, the person actually looks at every data set that comes in. He's able to identify, he's able to tag it, and we use that label back into the system, and then we try and build a model. Now, the issue with that is super slow. I mean, there are millions and millions of records every time your computer starts out a connection. How many of them will you be able to label it? Probably a company will die down, but he'll still be labeling it. So it'll be so slow. The other way we do it is we actually do something as an assisted labeling. Here, what we do is we cluster the data. We cluster the data based off features, and then we provide it to the analyst to identify different kinds of behaviors. And he could sample it. He could actually do some kind of a statistical sampling on top of it, and that actually helps him identify behavior and tag it. So then, based off these clusters, we are able to identify groups of behavior. And the clusters are deliberately kept small so that the behavior is identifiable uniquely, not necessarily in a grand fashion. And the way we deploy it is there's a machine learning model that works along, that ingests the same kind of data, your traffic logs, PCAPs, and alert data. And basically we have the information that basically comes out is whether this kind of a traffic is suspicious or not. It helps us identify whether we have had some kind of an attack, anything similar to something that looks like an attack, and that's kind of helpful. The way this kind of assists is in multiple ways. The model works in association with different IDS and IPS systems. And the reason why this works in such a way is that security community is kind of paranoid. And I tell you with a lot of responsibility. And the reason is because we believe in rule-based systems. We believe that even if we miss that one attack, that's it. It's the end of it. And it is true, because we can never approach a security issue probabilistically, because that one attack might be the biggest attack that you ever have. Which is why most of the models that we deploy are usually in conjunction with the IDS or the IPS systems that are actually helping identify these things through behaviors. But we've definitely seen a huge amount of difference in terms of how the models behave and how the IDS and the IPS systems actually behave. So that's kind of a big advantage. The other way is for someone who wants some amount of eyes on it, not necessarily automate the process. We have these feeds that actually go into security operations centers across different organizations, and they help you identify whether our classification is right or wrong. And this kind of ties back into the assisted labeling process as well, where the person can actually label it. They can also see how the output comes out. Kind of helps do both things at the same time. And so yeah, this is how we implement the model. The next version of that we are working on, the next version of the modeling that we are working on is basically we are having a complex algorithm where we don't necessarily have to label it, but we can purely do it based off without labels, purely be able to identify by feature engineering, really strong features which help us identify different models. That actually is still work in progress. So it's literally got one slide, that's it, nothing else. Thank you. So any questions, anything at all? It is password. Good, thank you. Oh, sorry, there was a question, yes. Sir. So the rate at which we deploy new models is actually 15 days once. So we revisit the features every 7 days. So we at half the rate of at which model gets deployed. Okay, thank you.